Um, so for this video, we'll talk a little bit about Newton's first law and inertial frames of reference, and then end it with example problem number 2. Okay, so to start out, as you can see, we'll just go over Newton's first law, which is an object in motion stays in motion, while an object at rest stays at rest. This is unless the object is acted upon by another force, such as gravity or another external force. But other than that, that's Newton's law, and you should write that down so you remember it. Yeah, pretty simple for Newton's first law. And then next we'll talk about inertial frames of reference. So, just to put it simply, an inertial frame is when there's constant velocity. So that means acceleration, as you can see, will be equal to 0. So just to give a little example of a situation where it may or may not be an inertial frame. So if a person is standing in an elevator and they're standing on a scale, and the scale reads 110 newtons, and that's the normal force, but the mg reading is 100 newtons, so those aren't equal. Would this be an inertial frame of reference? An inertial frame. So it's not an inertial frame because the normal force and force of gravity mg, those need to be the same, or else if they're not the same, in this case, this is one of those cases where they're not the same, then acceleration is not 0, so then it's not constant velocity. The elevator would be accelerating, and it's not an inertial frame. So now we're going to go to the example problem number 2. So student 1 is standing on a cart holding a small stone, while student 2 is standing at rest on the ground. As shown in the figure above, the cart is moving at a constant speed v in the positive x direction, as indicated by the coordinate system shown. Student 1 drops the stone precisely when passing student 2. Which of the following best represents the path of the falling stone relative to student 1 and the path of the falling stone relative to student 2? So as you can see on the left, we see the path. The representations relative to student 1, on the right is relative to student 2. So as we think about this, you can see the depiction, the little drawing up at the top. So as we think about this, the stone is being held by student 1. So, and on a moving cart. So that we know that student 1, we'll just draw this. Student 1, I'll put a little number 1 on the student's head, and is moving with a velocity in the positive x direction, because there's on a cart which is moving this direction. So, and also the stone they're holding is moving this direction. So, all the cart, the student, and the stone all have the same velocity in the x direction. And student 2 is standing right here, without the stone, of course. So, pretty much, we can, for this one, it's pretty straightforward. We can, as the stone is going to be dropped, we have to remember Newton's first law. So obviously, when the stone is going to be dropped, it's going to go down towards the ground. But as you remember Newton's first law, an object in motion stays in motion. So the stone is moving at the same x velocity as the student. So it's going to remain in motion because it's already in motion. So as the student and the cart move forward, the stone will too, but the stone will just so in terms of exposition, it'll be the same as the student the stone will have, but it'll just go down. So we know that in terms of the relationship between student 1 and the stone will just go straight down, right? Whereas for student 2, we can see right here, student 2 isn't moving in the x direction, so the stone will remain in motion in the positive x direction. So although the stone will be moving towards the ground, it'll remain in motion and go like sort of like that in relation to student 2, because see this x component right here, that'll remain moving. And you can see right here, answer C, student 1 straight down, student 2 has that x component because student 2 is not moving but the stone is.